afternoon everyone. So, today in this lecture I am going to introduce the Z transform. As I have mentioned, Z transforms are widely applicable transforms, and specifically in when we have to evaluate some test cases in signal processing or some specific examples in electronics and communication systems. Now, the most unique aspect of this transform is that this particular transform is defined as a discrete sum rather than the continuous integral that we have so far introduced in all my other previous transforms. So, let us continue our discussion on Z transforms. So, as I have mentioned, and as some of the students may already know, Z transforms have wide ranging applications in communications, and digital systems, and it is also applicable. Well, as I said, the most unique part about this Z transform is that it is going to be applied for linear time invariant discrete system. So, linear time invariant discrete system. Okay. As opposed to some of the other all the other transforms that we have seen in all our previous discussions in our earlier lectures. So, let me, before I introduce the definition of Z transform, let me start with some background. So, I am going to revisit my discussion on dynamic linear systems and introduced some more terms in greater details. Okay. So, I am revisiting my students who have seen through my lectures on Fourier transform, specifically in the example where I discussed Shannon sampling theorem, must have encountered some of the terms that I am going to go in slightly more detail now. So, I am going to revisit terms like dynamic linear system, impulse response function, and so on. So, when I talk about a system, so I am starting with the most basic definition. So, when I talk about a system, I say the system is like a black box. It is like a device where we feed in an input, and let us say the input is in the form of a signal, right. So, I call that signal to be the function f of t, and it goes through the system. So, the system is like a black box, and what we get is an output signal, or also known as the response function termed by this continuous function g t. Okay. So, which means that my output is when I say output, I denote the output signal. The output is completely determined by my input signal and my system characteristics. Okay. So, my output is completely determined by my input and system characteristics. Okay. So, in terms of math notation, I say that my output g of t is equal to L times the input, where L is an operator which is described by the system. So, operator described by whatever system I am talking about, described by the system. Okay. So, I can write down my output signal as a relation in terms of the input signal, more often than not like an ODE type of a of an equation ODE or a PDE, where L is the operator which is described by the specific system. For example, the system could be an LCR circuit or an LR circuit and so on. So, let us say, so I call this L as my transformation operator, transformation operator. And now I also assume that L is a linear operator. So, L is a linear operator, and L, well, this being a linear operator, it is going to satisfy the principle of superposition. So, satisfies superposition principle. Okay. So, these are some of the things that we already know. So, I am just outlining some of these definitions again to come to the definition of Z transform. So, then let us now reintroduce my idea of delta function. So, because we are going to describe my continuous function using a discrete sum of delta functions. So, again let us come to the delta functions itself. So, let me start by outlining some fundamental properties of delta function. I see that I have this following relation that holds true. So, delta f of t for any function, for any function f of t, I know that f of t times delta of t minus t n is f of t n times delta of t minus t n. Okay. So, all I need to make sure is that f is continuous in the interval around the time point t n. It is continuous around the interval in the interval around the time point t n. Okay. So, then we will see that almost all the fields involving sampling theory or pulse modulation systems, or in fact including systems including feedback like the filters or ECG cardiogram, they all use this fundamental property of delta function. So, then coming, let me just call this property by 1, because I will be using this time and again. So, if I were to get the output function or the output signal, I use this property of delta function. To get the output response, I sum 1 over all n, right. So, whatever time points that I have the information, I sum it over all such time points. So, I get that my output, let us denote it by f star of t, that will be equal to the summation n from negative infinity to infinity f of t delta of t minus t n. So, I see that this is also, using the property 1, this is also equal to summation n from negative infinity to infinity f of t n delta of t minus t n. Okay. I also call this as, from now on we see that this output from this sum, we see that the output can be written as the sum of the input functions f n summed over discretely over specific time points t n. So, if my input signals were unity, then my discrete signals were completely represented by this delta function. So, which means for input equal to 1, the delta functions denote my input at time points t n. So, I call these delta functions as my unit impulse function. Okay. So, why? Because it has, well, it is an impulsive function. Well, it gives an impulse at each time point t equal to t n for the function with an amplitude equal to 1. So, then so let me call this expression, this summation expression, by let us say 1 prime. So, 1 prime, what does 1 prime denotes? So, 1 prime denotes that the sampled function is approximately represented by a train of unit impulse function. So, my sampled function is approximately represented by a train of unit impulse functions. Okay. So, we see that my sampled function is represented by these unit impulse functions, which is the delta functions. Now, let us now further make another approximation. Let us say that I am going to use my time points, put t n to be equally spaced. So, let us say my time points are spaced equally with interval capital T. So, if I do that, then in this particular case the series n from negative infinity to infinity is also known as the impulse train. This is, in this specific case, I denote this summation as my impulse train. So, all these terms are quite prevalent in signal processing. So, what do I mean by impulse train? Which means that suppose if I were to measure these signals at these time points t n, which are equally spaced. So, let us say this is at 0, negative t, negative 2 t, to t to 2 t, and so on. I see that my impulse functions have an integral value equal to 1. So, they are all equal and they arrive at equal intervals of time. So, this is a unit impulse function at equidistant point of time known as the impulse train. Okay. So, moving on, I see that so then again I am going to use 1 and I am going to use the fact that my time points are equally spaced, my time points t n are equally spaced to arrive at, and also further I am going to use that my period t is small. Let us say I denote the small period as d tau. Okay. So, then if I use my expression 1, I come to the conclusion that f of t is equal to f of t n times delta of t minus n d tau. My period is small given by d tau. So, this is t minus t n. Well, so this is going to be f of t n. So, let me rewrite this expression. My sampled function is f of n d tau. So, that is my t n times delta of t minus n d tau divided by. So, let me just sum it up using my expression. So, I am using 1 prime instead of 1. So, I am going to sum it up, and the resultant that I have is, so sum from negative infinity to infinity divided by the sum from negative infinity to infinity of this chain of delta functions. So, this is t minus n d tau. So, I see that, so let me, so that is what we have for from 1. So, then next I am going to, let me call this as my expression 2. So, I am going to multiply 2 by n d tau, and I am going to replace I am going to replace n d tau by the variable d tau. So, what I am doing is I am notice that this is an summation over an infinite domain. So, this is discrete sum. So, discrete sum written in the form of a series. The series written in for discrete values of the function evaluated at discrete time points. So, what I am trying to do is that I am slowly going to change this summation to an integral. So, when we do that, I get my sampled function to be equal to integral negative infinity to infinity. So, I have already made my points of sampling n d tau to be sufficiently small, so that my summation can be safely changed into an integral, and I get that my function f of t can be written in this integral representation f of tau delta of t minus tau d tau divided by another integral from negative infinity to infinity delta of t minus tau d tau, and I know from the property of delta function that this integral is 1. So, what I have shown here is that this integral is negative infinity to infinity f of tau delta of t minus tau d tau. Okay. So, this particular representation of f of t, this let me call this as expression as my 3. So, 3 is the integral equivalent of 1 prime. Okay. So, that 1 prime was the discrete case and 3 is the integral equivalent. So, then we see that, so if we look at 3 carefully, we see that if my left hand side can be denoted as my output function. So, let us say that the LHS of 3, if I denote it by the output function, let us call that this is g of t, then the output function can be represented as this convolution of the input signal with this delta function. So, what I am saying is the following. So, if the LHS of 3 can be represented by the output function, let us denote it by another new function g of t. So, my g of t is the output of the system and my f of t is the input of the system, which is what the convention that I started with. So, in that case my g of t is integral negative infinity to infinity f of tau delta of t minus tau d tau. Okay. So, if I have a system, so what this relation shows, that if I have a system where my individual signals are represented by these unit impulse functions, then my output can be represented from the input signal by this following integral. Okay. And then I can see that this particular integral is nothing but the Fourier convolution integral. Okay. So, let me call this as 4. So, 4 is the Fourier convolution, right. So, what I have is that the output is nothing but f convolve with h, where my function h is delta function, the delta function, okay. And this is in the convolution is in the Fourier sense. Okay. So far we have described convolution in many different ways related to each of the transforms. So, this is in the Fourier sense. Okay. So, then now, so again coming back to, so again if I revisit my expression 1 in my previous slide, and I take my function h of t to be this summation, the summation of this train of unit impulse function or unit impulse train, right. So, from n from negative infinity to infinity. So, h of t is the summation of delta function or the impulse, sorry, this is the impulse train function. So, then what I have is, that my output, if I were to represent my output g of t is f of t convolve with h of t, to be given by f of t convolve with the summation of this series times delta of t minus n t. And if I were to write this as the convolution sense using the convolution integral, I get that this is integral negative infinity to infinity f of t. Well, I am going to take the summation out of the integral. So, summation from negative infinity to infinity, and f of, well, so the convolution will be f of tau delta of t minus n t minus tau d tau. So, that is my convolution. So, we see that again this is a convolution with respect to the delta function, and I can evaluate the interior integral to get to the conclusion that I have the summation as follows. So, this is f of t minus n t, and that is it. So, here I have used the fact that delta of, well, x minus a is the delta of a minus x. So, my a is this following quantity. So, delta of a minus x is delta of x minus a. Okay. So, then what I have shown here is the following. So, this particular expression, let me call this as 5. I have shown here is that the output of any signal can be represented by an infinite sum at discrete points of time of infinite sum of the input, infinite discrete sum of the input at regular points of time interval. So, the output is the superposition, it is the superposition of all translations of f. Okay. So, which means that my output can be represented in the form of a discrete sum of input. Okay. So, then, well, so from here I want to highlight the fact that more often than not my variable t that I am using in this all these expression, most of the time they denote the time point, and most of my time point calculations start at t equal to 0. So, I assume that t is greater than equal to 0. So, that simplifies this summation from 0 to infinity. So, what I just said is the following. So, in general my input is applied only for t greater than equal to 0, and h of t is 0 for t less than 0. So, I have applied the input in such a way, well, the input is applied in such a way that this if I were to retain this sum, I take this input signal in such a way that my delta, my unit impulse response functions are taken to be 0 in the negative time interval. So, then I can extend this particular case to the case discussed by this expression 5. Okay. So, then well, if this is the case that t is greater than 0, then my output, if we see the output by our expression 4, it can be written, it can be shown that this is integral, it is integral from 0 to t. Well, t could be any point of time up to which we want to calculate our output. So, it is integral from 0 to t f of tau h of t minus tau d tau. So, our output is the convolution of the input, but this is in the Laplace sense, not in the Fourier sense. So, this is in the Laplace sense of convolution. Why? Because I have completely discarded the negative half of the integral. Okay. So, moving on, if I were to write this output, so let me write this expression again. So, what I have just highlighted. So, g is 0 to t f of tau h of t minus tau d tau. So, this is nothing but f star g in the Laplace sense. Okay. So, the convolution in the Laplace sense, Laplace transform sense. So, if I were to write this output, this integral form in the discrete notation, then in that case, so in the discrete notation, the discrete case, my output or my sampled function, can be shown to be, let me call this, I am going to distinguish it from g t, because that is the continuous case. So, my output or sampled function f star t is f of t summation, well, n from 0 to infinity delta of t minus n t. Okay. So, well, and so this is also equal to the summation n from 0 to infinity f of n t. So, I am using my fundamental property of delta function. So, using 1. So, this is also equal to f of n t delta of t minus n t. Okay. So, this is the discrete case of the above expression in the integral form. So, if we have a signal which is only measured at real times, which will be positive, then we will use the following discrete summation to represent the output signal. Okay. So, then so far I have just created, I have provided you some of the basic backgrounds, and from now on I am going to describe my Z transform using these discrete summation. So, moving on,